My name is Sandra Cremier, and this is the third lab for Physics 2. So to introduce, the purpose of this lab is to measure the magnetic field of a bar magnet by understanding properties like the distance dependence and the BSO-Bart law to understand the magnetic dipole moment. Then furtherly, we will develop skills in computational modeling and understanding linearization. These are some of the results previewed, but I think that the most notable ones are the difference between the magnitude of the magnetic field at 45 degrees off axis, because for the experiment and the computational model, they vary, but we will discuss this differences later. So some fundamental physics principles to understand the BSO-Bart law and just the magnetic field in general, which is a vector describing the magnetic influence on moving electric charges, currents, and other magnetic materials from an observation location. And the magnetic field of a bar magnet and the magnetic field of a dipole, because we are assuming that the bar magnet is a dipole. And then these are some relevant formulas, which include the distance dependence and the BSO-Bart law. So the method and experiment, first we're going to go into the method. We put a bar magnet at one end of the east-west meter stick, then place the phone a few centimeters away from the magnet perpendicular to the meter stick and resting on top. Then we slide the phone across this axis until we find the maximum X component and the minimum Y component. Then we rotate the phone 90 degrees, and this time we slide it across this new axis to find the maximum Y value and the minimum X value. Then the assumptions for the physical model include that the bar magnet will act as a magnetic dipole, and the system includes the bar magnet, making everything else part of the surroundings. This means that there are no external magnetic fields interfering with the system. So this is the results for the experimental data. I will not go over them because they're very long, but we can see the graph for ln Bx versus ln R. And also we can see that the net magnetic field in Teslas is 5.4079 times 10 to the negative 5. Further calculations include the slope, the y-intercept, which is ln k, and then using logarithmic laws, we understand that k is equal to e to the power of negative 13.66. And then it gives us this. Using the BSO-Bart law, we can use these data to find mu, which is equal to 5.841 Newton meters per Tesla. And then the experimental observations I saw was that when the magnetometer is far away from the magnet, it measures near zero magnetic field in the X direction. And as the magnetometer moves closer to the magnet, the measured X component of the magnetic field increases. So for moving on to the computational model, first I noted down the constants and the observed values. And I used values from the experiment, so I am assuming that the experimental data is indeed correct. Then we move on to the visualization of the magnetic field by creating a function for the magnetic field in general. Then note that this scale is just a random number that made the visual look correct. And then we use distance from the experiment. Then we move on to the arrows, so the magnetic field on axis and then the magnetic field perpendicular to the axis. And lastly, we are visualizing the magnetic field 45 degrees off axis because that's what we want. And then these are the results. This is the visual I got, and then this are the values. But we can obviously see that there are sources of error because in the experiment, the magnitude of the magnetic field at 45 degrees was 5.408 times 10 to the negative 5. Whereas in the computational model, the magnitude of the magnetic field at 45 degrees was 4.61 times 10 to the negative 5. Other magnetic fields in the surroundings might have interacted with the values on the application. And there's also human error to account for it. For example, when moving the phone, movement might have not been fully straight because of small tremors or non-perfectly linear movements. And then moving on to the reflection, lastly, we have to consider what if you hadn't oriented your experiment to compensate for magnetic north. And I would personally expect that the results for BX and just the magnetic field in general would be less accurate because the magnetic field from the Earth would now be interfering with the results. Then if we were to stick two identical magnets together end to end and run the experiment again, I would expect the results to be multiplied by a scalar quantity, and I would also expect the results to increase because of a new magnetic dipole moment and a new magnetic field. but everything else, such as observation location and magnetic field of a single magnet, would remain equal. We just have to account for these new components. Thank you.